Hello students, in this video we'll find a conformal mapping from a strip onto the entire complex plane with two intervals deleted. Let's consider the map 5z, which is z plus e to the z. Let's prove that phi maps the strip z such that negative pi less than the imaginary part of z less than pi onto the complex plane onto C minus the union of two half-line segments, R1 and R2, R plus and R minus, where here R plus minus is the set of all A plus minus I pi, such that A is less than -1, like that. Okay, those are those strips. Okay, excellent. And so now here's our situation, right? So first thing we note is I note that phi of z bar is equal to phi of z bars like this, right? Because what is this? This, of course, is just z plus e to the z bar, which is just z bar plus e to the z bar, because I can break down e to the z into e to the x, real, cosine and sine, and so the result holds for this particular function. Okay, excellent. So we can restrict to this part of the strip, just the top of the strip. And note, of course, that the exponential, and we note, and just the upper half space minus r plus, where here pi is the upper half space. Okay, beautiful. All right, and so other thing to note is that second note is that e to the z by itself takes this strip onto the upper half space. Okay, excellent. So those two notes are going to help us out a lot. Okay, now they help us out in the following context. They allow me to build a Schwarz-Christoffel transformation to punch out a half line segment, right? A half ray, basically, right? And so here's what we're going to do. We're going to look at that ray, and so this, of course, is the point -1 plus I pi. There's the imaginary axis. There's I. Here's the real axis over here, and that's the point -1. And what I'm going to do is I want a Schwarz-Christoffel transformation to the upper half space minus this segment, right? That's what we want. So how are we going to build such a Schwarz-Christoffel transformation? We're going to think about a degenerate polygon. So what I'm going to do is I'm going to pick a point. I'm going to call this point over here W1. I'm going to pick a point over here W2, which is just -r for some real value r positive and very, very large, right? And what we're going to do is we're going to consider this region over here, like that. And so now the region we're punching out, so now this region's open, right? So this region now is open. Okay? We're going to map onto this region, the complement of this little triangular wedge that goes on forever, right? Okay, good. And so now what are these two exterior angles over here, right? So what I'm going to do is I'm going to map Z1, which is going to be -1. I'm going to map that onto W1. And I'm going to map Z2, which is going to be 0. I'm going to map that onto W2, okay? And we're going to let r go to infinity, and then r is going to go to infinity, right? And if r goes to infinity, then we're going to get that strip, the punctured strip that we want, okay? What are the exterior angles? So over here, the exterior angle is alpha, right? So alpha plus what in the limit? Plus 2 pi in the limit, right? This, of course, is r goes to infinity, is equal to pi. And that's going to force alpha to be -pi, which is going to be a positive exponent, right? And then as r goes to infinity, looks about beta. Remember, this is open over here now, right? That's my beta. So I know that beta plus 0 and the limit, of course, is equal to pi, and that forces beta to be pi. Great. Okay, so now I have my parameters for Schwarz-Christoffel, and so would the Schwarz-Christoffel mapping be onto this region with a slit. So now f prime of z will be equal to a, and then a z plus 1 gets a power of what? It gets a power of 1. And then z gets a power of -1. So this is going to be a times z plus 1 over z. And this is a rare instance when Schwarz-Christoffel simplifies a lot. 1 plus 1 over z. Oh, that's beautiful. So therefore, f of z is going to be a, and then I'm going to have a z plus a branch of the log of z, okay, which is, I probably punch up the negative imaginary axis, plus a constant b, right? Good. Well, what if we plug in -1 to this? If we plug in -1, we have to get to this point over here. So -1 plus I pi has to be equal to what? Has to be equal to a, -1 plus the log of -1, which is I pi, plus b. Okay, so this equation over here is going to force, and of course if you plug in 0 to this, you're going to have a problem, right? But you have to choose the right branch of log, right? If I plug in a very, very negative number, it's going to tell me that b has to be 0. This is going to force b to be equal to 0. It's going to force a, this also forces a to be equal to 1, because that's exactly the same thing over there. So our Schwarz-Christoffel mapping, so f of z, which is what? F of z is just going to be z plus log of z. Now you might say, how does this help us over here, right? So this maps the upper half space, which we're calling pi, onto what? Onto the complex plane, on the upper half space rather, excuse me, on the upper half space, minus what? Minus this ray r plus, right? Minus r plus. Good. And so now what can I do? Let me consider what? I'm going to plug into this function over here, e to the z, right? So what will f of e to the z be? F of e to the z is going to be what? F of e to the z is going to be e to the z plus the log of e to the z, which is z plus e to the z. Great. Now that's phi. So so this says that phi of z is what? Phi of z is f of e to the z. So it's a composition of two things. So what happens over here? So phi, if I do what? If I plug in the strip, z less than 0 less than imaginary part of z less than pi, where does e to the z take that strip? E to the z takes that strip to the upper half space. Then where does f via e to the z? Then where does f take the upper half space? F takes the upper half space onto gamma, pi rather, minus r plus. Beautiful, now we have the result, because by recognizing this as the composition of two maps, putting in one intermediate step, I'm now able to prove where the exponential map takes the strip. Now I'm going to use this reflection symmetry, right? So I can reflect the problem and get the result for free. Beautiful, right? So in other words, this is a common trick in conformal maps, right? Taking one conformal map as an intermediary to use the result. And then in this case, we use the degenerate form of the Schwarz-Christoffel mapping to get this beautiful result. So in general, if you want to punch out an interval from the complex plane, you need to use a degenerate Schwarz-Christoffel mapping. That's really, there are other ways to do it, but that's really the most traditional way of doing it. Very, very common technique. And so now what this gives me is a way of measuring streamlines in a situation where there's sort of two obstacles, right, in the entire complex plane to flow around, right? So you get beautiful streamlines if you simulate this. If you replace, in this mapping over here, if you replace z with t plus ic, where t goes between -infinity and infinity and c is a constant, those will be the streamlines for that region. So you get really beautiful sort of simulations from looking at this map. Thank you very much.